Okay, everyone, welcome to the second screencast for Chapter 6. We're still looking at dummy variables, but now we're going to be dealing with a multivariate OLS. All right, we're going to be dealing with not just one variable on the right-hand side, but multiple variables. So our dummy variable is still going to be whether you're in a category or not, right? Whether you have the trait that is the name of that variable, right, or not. But there's going to be other things going on in the regression. All right, so now we're going to start to deal with possibly if the dummy variable is our independent variable of interest, we're going to want to control for other things to know whether or not having the one for the independent variable is causal or not. Or in some cases, these dummy variables are going to be our control variables. All right, so here we go. So the first step we're going to take is we're still going to do a difference of means test, but we're going to do it with multivariate OLS. So this is going to be a difference of means, but controlling for something that we might think is confounding our original bivariate difference of means test, right? So maybe that difference of means test with height and gender that we saw in 6.1. What if we have a bunch of student athletes, right, in our data set? Maybe we want to throw in a control for that, all right? Or something like that. But we'll see a couple of examples here. So in general, here is what a difference of means test, but with some controls would look like. All right. So I've got the dummy variable right up front here. So in this case, this is going to be my independent variable of interest, but I'm going to control for something that I think if I leave out this x, it's in the error term, right? If it's correlated with y and my independent variable of interest here, then I can't give any sort of real causal interpretation to beta 1 hat. Now, it's still a difference of means test. It still works for that, but it won't let me say anything more generally about the causal effect. I can't give any support for a causal theory that being 1 causes a change in y. All I would be able to say is if you have a 1, there's a statistically significant difference in y, and that's a very different thing for all the reasons we've talked about for the whole class. So I'm going to pull out this x out of the error term and put it in here to try to get rid of the bias, the endogeneity, the omitted variable bias in my estimate of beta 1, my beta 1 hat. So for a general model, here's what it looks like. The dummy variable here and then the control here. And this control, for now, is going to be a continuous control. It's not going to be another dummy variable, all right? It's going to be something that is can take on a bunch of different values, not just 0 and 1. So when you run this regression, what you're going to get is two lines, two best fit lines, that both are going to have a slope of beta 2 hat, all right? And they're going to be separated by beta 1 hat, all right, by the effect of being in this category or not for all values of x. And so that's kind of hard to picture, so let's take a look at this regression. So we're going to say, we're going to look at a particular model with, this is back the one I introduced in the last screencast, the home field advantage for these two crap football teams from Manchester, Man City and Man United. So does home field advantage let Manchester City score more goals? We're going to use a dummy variable of 1 for home games. All right. So here is this regression. Goal differential. Remember, goal differential is number of goals you score in a given game minus the number of goals you allow during a given game. Right. So it's the goal differential. That's what it is. And then we have our dummy variable here. This is sort of looking like what we're looking for here is home field advantage, right? Is this going to be statistically significant? And then can we say anything causal about it? And so for this regression, if we just ran this one, let's assume we didn't have, trying to get my thing here. What if we didn't have this for a second and we just had this? Well, we could say whether or not there was a difference of the average goal differential for home games versus away games. We could definitely say that. We could use the measure of statistical significance, the T or the P, that we would get back from R, and we could then say we could reject the null or fail to reject the null. The null would be that home field advantage is not a thing. if we reject it, then we could interpret it and say, on average, for home games, the goal differential is this much, probably higher than the away games, right? We could do that, a difference means test, but we wouldn't really know about home field advantage. Why? Well, there can be all sorts of things lurking in this error term that could be correlated with both of these things. Now, in this case, I don't necessarily think opponent quality is correlated with both, but this is still the example that Bailey chose, and I think it does show us a couple of other things. So here we go. Here's the results. Now, again, this is home getting a 1. So home field in the data set, that meant home was probably the name of the variable, and it got a 1 if it was a home game. So the rows in this data set are games. The first column in the data set is home. 1 if it's a home game for a game, and 0 otherwise. And then opponent quality is over here. And we won't go into how that's measured exactly. You can, Dr. Lynch in his sports econ class or something, he goes into a lot of these different measures for soccer and a lot of other things. He's a fan of another crap soccer team, one from London in his case. But opponent quality, we'll just take that measure as given. So we've controlled for the opponent quality here. And now what is the effect of being at home? All right. So we run this regression, and what we actually get are 2 different best fit lines. One for all the home games and one for all the away games. And the difference is going to be beta 1 hat. And the easiest way to picture this is to picture it literally like this. So here is what we have here. So let me talk you through what's going on here. So here we have opponent quality as the X, don't even call it X. Opponent quality is the horizontal axis here. So the opponent quality here ranges from -32 to +40 for, well, even higher than that. Here's one that's even higher in our data set. It's probably a measure from -50 to 50 if I had to guess. But for Man City, these are all of the games. Each dot is a game. And I've color-coded them here, or Bailey has, as, or not color-coded him, shape-coded them as a circle for a home game and a square for a, if it's an away game, home equals 0. And so we don't necessarily have the a axis or a dimension for the home game. We've just color-coded the scatter plots. And so these are the 2 best fit lines through the different clouds of dots. This is the best fit line through the cloud of dots for the home game, for the circle cloud of dots. And this is the best fit line through the square cloud of dots. All right. In this version, they must be parallel. We're going to get to that in a later section. Well, what if I don't want to force them to be parallel? We'll come back to that. But for now, let's just make sure we get this down. So the slope is the same. The effect of opponent quality on goal differential is the same whether or not it's a home game or away game. That's what this parallel slope means. All right. And in fact, we know what the slope of that is. It is this. It is statistically significant. T is bigger than 2. And as opponent quality increases, for every 1 unit increase in opponent quality, goal differential falls by 0.025. The better team you play, the less your goal differential is going to be. Why? Because they're going to be scoring goals on you and keeping you from scoring goals. All right. So that is the slope of this line. The difference between these 2 lines is beta 1 hat. All right. That's the shift. That's the effect of being at home. The home games are higher, and we can see that here in the table. Home, on average, for home games, Man City scores 1.0, well, no, Man City's goal differential is on average 1.026 goals higher, and it is statistically significant, all right? Now remember, the intercept here, why is it doing the dot, dot, dot line over here to the middle? Because the intercept is where the X here gets a 0 value, where opponent quality is 0. That's where the beta naught hat comes from. But in this data set, the opponent quality does have negative values. All right. So I kind of went over this earlier in the semester, and we haven't seen too many cases of it yet. So this is a good reminder that the intercept is, the value of it is at X, or sorry, is at the horizontal variable's value of 0. And then this is, quote unquote, the intercept for the home games. All right, we add the two effects together. What is it? It's the average goal differential for home games. This is the average differential for away games, right? Where did we see that before? Right here. This is the constant. How do I know how to interpret it? This is the average of the dependent variable, goal differential, for the 0 group, for the group that got 0 for home, controlling for opponent quality. All right? That's how you interpret the intercept right here. And then this is the average goal differential for the group that got the 1, that for the home games, controlling for opponent quality. The intercepts differ by how much? By beta 1 hat, by the average difference between home games and away games. So this is a difference of means test controlling for 1. We could actually control for other variables if we wanted to. But you've probably done one like this before. Often after you do a difference of means test in a basic stats class, then you do one where you break it out according to another variable. This is sometimes called a conditional difference of means test. All right? And so this is in fact what we've done here. We've done a conditional difference of means test. The difference of means between home and away games, but conditional on controlling for opponent quality. All right? So that's going to be the end of section 6.2, the end of the second section of chapter 6. And in the next section, we're going to look at other things we can do with dummy variables in multivariate OLS. So far, we've done plain old difference of means test, controlling for nothing. In this section, we did a conditional difference of means test, a difference of means test, but controlling for something that we might think matters for our question. We're doing a difference of means test for a reason, and we may instantly think of some sort of confounding variable. And so we want to control for that to see if I take off the effect of that, do I still get a statistically significant difference between the 1 group and the 0 group? And in fact, for this one, we did. So in the next section, we're going to look at a different way to use dummy variables.